Today we will talk about, two actually somewhat connected topics, or I would say Fibonacci is some kind of a subset within a broader set called ratios. Fibonacci series is something Bhama will talk about, followed by Sendil, who will talk about ratios. And I wouldn't take 15 minutes, so Sendil, you can take more time if you need. And I have a couple of slides I would like to share in terms of how Fibonacci series is applied to the real world. And finally, we will have a good 35-40 minutes where we will spend on Priya's practical problem solving, which we will open up. That's a very specific topic which she wanted to, or a specific child she wanted to talk about. And we will try and open the topic into a slightly broader a broader question or a broader topic, and see how we can interpret it and analyze it and take decisions with it. Yeah. Mama, if you're good, I will start sharing your slides.
Yeah.
Let me just go on mute. By trying to go on mute, I stopped sharing.
Yeah. Fibonacci numbers are named after Leonardo of Pisa. His other name was Fibonacci, and he's one of the greatest European mathematicians who lived in the 12th century. So much before the others, the 14th, 15th and all that. So he introduced the decimal system, the Hindu-Arabic system, and the idea of place value to Europe. And before that, they used to use Roman numerals. So the original problem that Fibonacci investigated and wrote about in his book was about how fast rabbits could breed in ideal circumstances. So suppose we have a newly born pair of rabbits, one male and one female, and they are put in a field. So rabbits, they mate at the age of 1 month, and at the end of the second month, a female can produce another pair of rabbits. So suppose that our rabbits never die in ideal circumstances, and then the female always produces one new pair, one male and one female, every month from the second month on. And so the puzzle that Fibonacci posed was, how many pairs of rabbits will there be in 1 year? So at the end of we start off with 1, and then at the end of this first month, they mate, and there are still 1 pair. At the end of the second month, the female is going to produce a new pair. So now there are 2 pairs of rabbits in the field. At the end of the third month, the original female is going to produce a second pair, produces a new pair, and produces a second pair. And so there are now 3 pairs in the field. At the end of the fourth month, the original female has produced yet another new pair, and the female that is born 2 months ago produces a first pair. So totally 5 pairs. So basically, the number of rabbit pairs for the next month is the number of rabbit pairs for this month, because none of them die, right? And the number of rabbit pairs the previous month, because all of them are now going to produce a new pair each. So the Fibonacci sequence is recursively defined in this way. The next Fibonacci number is found by adding the previous 2 Fibonacci numbers. So if we start off with a 0 and a 1, this is F0 and F1. And then the second Fibonacci number, F2, is nothing but 0 plus 1, that is 1. The third one, F3, is 1 plus 1, that is 2, and so on. So basically, Fn is defined recursively as Fn minus 1 plus Fn minus 2. And there are several properties of Fibonacci numbers. For example, the consecutive Fibonacci numbers are always relatively prime. 5 and 8 are prime, relatively prime. 8 and 13 have no common factors. So, and like this, there are many properties, but since in this session, we are going to be exploring ratios, we are going to look at some very interesting ratios related to Fibonacci numbers. So the golden ratio, you might have heard of this, and this is denoted by the Greek letter phi. And this is an irrational number, and it approximately equals to some 1.618, etc., etc. The decimals go on forever. So how do we get this number? The geometry behind the golden ratio is this. Say we divide a line into two parts, A and B, in such a way that the ratio of A is to B is also equal to the ratio of the whole length A plus B divided by the long part, that is A. So basically we are saying A plus B by A should be equal to A by B. And yeah, this can be an exploratory activity for children. Ask them to draw a line segment, ask them to find a point on it, such that they divide into two parts, A and B, such that this ratio, this equality holds. And if we take A by B as phi, we get phi is equal to 1 plus 1 over phi, right? So the golden ratio can be defined in terms of itself. That's what its speciality is. And it just reduces to a quadratic equation. And by rearranging the terms, if we solve this, we get phi as nothing but 1 plus root phi, the whole thing by 2. And that is 1.618 something. And next, please. Yeah, what is the relationship between this and the Fibonacci numbers? So if you take any successive Fibonacci numbers, we have seen that they are relatively prime, right? And the ratio comes very close to this golden ratio. In fact, the bigger the pair of Fibonacci numbers, the closer the approximation. And next, please. Any rectangle formed which has sides that has the ratio of phi is called the golden rectangle. So what we should have is, if we have one side of a rectangle as 1, the other side should be equal to 5. And this rectangle is very pleasing to the eye and is often used, typical sizes for frames and paintings and all that. So we saw what a golden rectangle is, but don't you think it will be difficult to draw the perfect golden rectangle because phi is irrational and with values like root 5, square root 5. But then it can be done in this beautiful manner, like, take a square of side length 1 shown in red, and then if you take the midpoint of the base and then join this point to the opposite corner of the square shown in black arrow. And this has a length root 5 by 2, right? Because it's a side of the right angle triangle of sides 1 and 0.5. So by Pythagoras, we get root 5 by 2. And since phi is nothing but half plus root of 5 by 2, if you take an arc as shown as a radius root 5 by 2 and we extend one side of the square shown in blue, we get the longer side of the rectangle where it meets, that's the longer side, that is nothing but 1 plus, that is nothing but 5, 1 plus root 5, the whole thing by 2. And the other side of the rectangle is 1. So in this way, we can construct the perfect golden rectangle. And that's a rectangle colored in light brown here. Then Kepler, the mathematician, he saw this quadratic equation, phi squared minus phi minus 1 is equal to 0. It inspired him to create this right angle triangle having sides root phi and 1, right? So the hypotenuse is phi squared. So, and this is something special, right? Because it links Pythagoras and phi together, and the ratio of the sides is 1 is to root phi is to phi, and this makes a geometric sequence, geometric progression. And many Egyptian pyramids, next please. The Egyptian pyramids, including the Great Pyramid of Giza, they closely have this proportion and they are called the golden pyramids. The ratio of B is to H is to A is 1 is to root phi is to phi. This is a beautiful activity which all the children will enjoy. And we can make this, we can make squares of the Fibonacci numbers as sides, and then we get a beautiful, fabulous spiral like this. So take any square paper, start off with two 1 into 1 squares side by side, as shown in step 1 in magenta and blue, right? And then 1 plus 1 makes 2, right? And so we can draw this 2 by 2 square next to it, the yellow squares shown in step 2. And then each time we can form bigger and bigger rectangles. So 1 plus 2 makes 3. So you can attach a 3 by 3 square as shown in step 3 in green and so on. So these rectangles are made by the Fibonacci numbers 1, 1, 2, then 3, then 5, and so on. And then these are all approximations of the golden rectangles, right? Because as they grow, they get closer and closer to the golden rectangle. And then we can draw this awesome spiral by connecting the opposite corners as shown. We get a shape very similar to the conch shell that is found in nature. So these are some exciting GIFs, and I just wanted to put them in. The first is unraveling of the rectangles made by the Fibonacci numbers. The second one, it just zooms in into the golden spiral. Yeah, it looks totally beautiful.
Feels like fractal, no? The second one.
Yeah, it is.
It is, yeah.
So here are some more insights into this magical number 5. So it is a fraction, and this fraction can be expanded. So each time we replace 5 by 1 plus 1 over 5, and it goes on and on forever, and it's called a continued fraction. And this phi is said to be more irrational than the other irrational constants that we know, like pi, that is the ratio of a circumference to the diameter, and e, the constant to show natural growth. Also, since 1 by phi is the multiplicative inverse of phi, right? And this is got by just subtracting 1 from phi. So the inverse of a number is just the decimals left over after you remove the 1. And that is something little crazy, right? And we'll see how this is interpreted in nature in the next few slides. So if we look at the central part of a sunflower, which has the seeds like closely packed, we see that there are many spirals in it if you look closely. And why is it so? Why do plants grow new cells in spirals? So the spiral happens naturally because each new cell is formed after a turn. So there's a new cell formed, and then it turns a bit, and then another new cell, and then again a turn. And why does it turn like this, and how far to turn? So if we don't turn at all, right, all the new cells will be formed in a straight line, as shown in the bottom left. But that is a very poor design, right? You can't pack many seeds this way. So what we want is something round that will hold together with no gaps as far as possible. So what happens if we try 1/4 the rotation? The cells will be formed at right angles as shown in the bottom second figure. And a 0.3 rotation will be shown, like we'll have 10 arms approximately, and the seeds will all be aligned with huge gaps in between. But then a 0.382 turn or a 0.618 rotation, that is basically the decimal part of phi, or the multiplicative inverse of phi, it gives rise to this spiral and this perfect packing. And it's the best way to make a pattern with no gaps from start to end in the form of a circle. And this, in terms of degrees, is 137.5 degrees, and it's called a golden angle. And that is why the irrational number 5 appears so much oftener in nature, because it's not close to any fraction. The other common irrational constants like pi and e are close to fractions. Pi can be replaced by 22 by 7, right? And the decimal part of pi is very close to 1 by 7. So each time, if suppose it turns as 1 by 7th of a rotation, right? The packing will look like 7 arms, and it's not an optimal packing. Again, E is irrational, and that's very close to 5 by 7, the decimal part of it. So, and that's why phi seems to be, it's considered to be more irrational than pi or e. It's not close to any fraction. And that's why the sunflower seeds are arranged like, this pretty spiral pattern. And here we can count clockwise, there are 13 spirals coming out, and anti-clockwise there are 8. So the angle between successive florets or petals or the leaves in many plants is this golden angle, 137.5. And this makes them grow in spirals. So when this happens, the new leaves are not just above the old leaves. So they are all shifted slightly. So they don't block the sun from the older leaves. And it allows a maximum number of rain or dew to get directed to the roots. And pine cones are good at Fibonacci numbers too. So you'll see like distinct spirals in a pine cone, and the number here in each direction are 8 and 13, and both are Fibonacci numbers. And when this occurs, the angle between the consecutive scales in a pine cone, it is like that 137.5 degrees. And this is the optimal packing of scales. And similarly, cauliflowers and many petals and flowers, they're all Fibonacci numbers, like buttercups are 5, petals, daisies are 34 or 55, marigolds are 13, and so on. Our human body proportions are in the golden ratio too. So if we stretch out our hand and measure the different arm lengths as shown, like shoulder to elbow or elbow to the tips of our fingers and so on, they all veer towards a golden ratio. Like the orange to red is a golden ratio, green to purple line is a golden ratio. And the picture on the right by the famous artist Leonardo da Vinci is called the Vitruvian Man. And he showed that in a perfect man, supposedly there are all these different measurements that follow the golden ratio. And Senthil mentioned in his first class of measurements, right? Children measuring their span, cubit, foot, etc. And so this can be a good activity for children. How close to the golden ratio do they come with respect to their body parts? And it's a very good exercise to reinforce ratios and division, multiplication, decimals, and so many other basic concepts in math. It just makes math come alive. So many buildings and artworks have the golden ratio in them, such as the Parthenon in Greece, Taj Mahal, the Notre Dame Church in Paris. And it's not really known if it was designed that way. It just looks, you can find golden ratios in them. Children can be asked to look at pictures of these famous constructions and then asked to discover the various golden ratios they can find. We can even find the golden spiral in Vinci's Mona Lisa. The pentagram is the mathematical name given to a symmetrical 5-pointed star that fits inside a regular pentagon, and that can be got by drawing corners of the pentagon. So the pentagram is, famous as a magical or a holy symbol in many religions. It has special significance. And here again, the golden ratio stands out. So if you take the ratios of the different colored segment lengths, like red to green is a golden ratio, green to blue, blue to purple, they're all golden ratios. The diagonals in the pentagram to the side of the regular pentagon. So the diagonal to the side of the regular pentagon is again a golden ratio. And the pentagon spiral on the right can be drawn by starting off with a pentagram inside a pentagon. And then to draw the next one, use the side of this pentagon as the side of the next pentagram to maintain the same ratio. And you continue like this. The pentagram also has 5 triangles at its end, right? And these are the golden triangles as we shown at the bottom center, and with which we can again construct the cone spiral. The pentagram fractal is shown on the top, and this is made by repeated operation of constructing a pentagram from each of the golden triangles in a recursive manner.
Truly boggles the mind.
Yeah, so all of these, yeah, can be adapted as exploratory activities for grade 6 to 10. And yeah, if there's anything you want to know a little more, or how this can be, made into a worksheet for children, yeah, so please don't hesitate to get in touch with us on our WhatsApp group. Thank you.
Thank you. Thank you, Bama. If there are any questions, we'll keep it to the end. We will move straight into Sendil's part. Sendil, are you ready?
Yeah.
Okay.
Can you hear?
Yes, we can.
Thanks, Mama. That was beautiful, actually. It is so nice to see all the Fibonacci things and the golden ratio. The only thing is sometimes the beauty of the face, sometimes they say it's golden ratio or something, but sometimes it's not. And some of the best plastic surgery industries are working with that. Other than that, everything else is so nicely put, and it was so great. And moving on to the ratios, I'm not trying to cover everything in a ratio or from concept wise. I'm trying to see what are all the different possibilities in a classroom which can actually deepen the idea of ratio in children. So the first thing is the possibilities in a classroom is just like you can talk about the ratio between the number of boys to number of girls and ratio of children to teachers in the school. How many? So let children copy down or just go do a survey of how many children are there in the whole school from across classes, and how many teachers, including class teachers and subject teachers, and sometimes even the whole helping staff and everyone. How many adults to how many children? Like, what's the ratio of the space? And how are the different ratios, and say how many children are coming from the neighborhood itself, immediate neighborhood, say 3 kilometers range, how many children are coming from far away, and what happens. So get all these details and then get them doing something like, so without looking at what is part to part or part to whole, we are just collecting the idea of ratio in them. And then there are various ways of doing ratios also. So one practical idea is the one which is my favorite when I collected for this last year. So I was looking for this kind of a game where in CISA, children can actually, based on their weight. So this is one exercise where apparently a boy weighing 30 kg is 5 feet away from the center of the CISA. So we can ask children to guess, where should the girl supposedly weighing 20 kg be sitting in order to make the Caesar balanced? Where would she sit? So, and then children start guessing. It's mostly this question they know by intuitively because they have been playing all through their childhood. But this Caesar is very interesting. If you see, there is some sort of a pump which is going to the ground. This is from that Bhimanahalli Higher Primary School in it's called Hegda Devana Kota, I think. So the district or the village in Karnataka, where this pump, every time when they play in the seesaw for say half an hour or something, it pumps and then what tank is getting filled in that school. And this idea has been developed by the SDMC, the School Development Management. So they proposed this idea and they have done this. Article featured in Better India with the two other stories where in one other school, the school principal.
Sendil, sorry to interrupt. Your internet is going bad again. I think the internet got cut off for Sendil. We'll just give him a minute or two. He should be here back soon. What I found interesting in this particular slide was you can see a little blue something here where I'm mousing over, and that apparently pumps the water. Every time children play, it sort of pumps water, which is interesting.
Sorry about that. It was not expected. So usually it's not like this. So it also covers two other stories. One is the savings account where the principal has encouraged children to deposit, probably even starting at 1 rupee. And the school had collected around 25,000 as their individual savings account tally. And and in other school, they were working on a vegetable garden, and all this were like at least 5 years or 5 to 10 years back. So it's a great story, and I hope the school and the SDMC would have done even better things. So it's very clear from that sum that girl is 2/3 the boy's weight. So she would sit 3 by 2 parts of 5 feet is where she would sit ideally. And then this we can work out. It's not more about the sum per se, but the intuition of where they would sit, and then we can work with more numbers a little later. But do more things with hands rather than just explaining. And so next, it's always favorite to do something and eat, to make something in the class and eat. So this activity of a 7-cup is one of the favorites. Even my sister here would make it whenever I go there and then have it. It's basically 7 cups. It's called 7-cup burfi because of the 7 cups, which makes the whole cake itself. As 3 parts of sugar, and then 1 part milk, 1 part besan, which is kadalamava, and then 1 part coconut and ghee. So of late, I have heard that instead of making 3 parts of sugar, you can make 2 parts sugar and then like 1 part something else which you like, which is probably other nuts, which can also add to the flavor. It's too much sugar is not so healthy. Sometimes this organic food people come and then bash me up. So this thing is first put part to part, understand them. It's like for 3 parts of sugar, it's 1 part of milk, 1 part of besan, 1 part of coconut, 1 part of tea. And then how many is the total number of parts? So as we make, children sort of understand, you can bring 7 cups itself, and then we are all putting like 3 cups, 3 cups is filled with sugar. Total number of cups is very clear, it's 7 cups. And how many out of 7 is sugar? It's 3 cups. So if 3 cups, then it's 1 cup milk. If 3 cups sugar, then 1 cup besan. So they get what is part to whole. And eventually what happens if instead of 3 cups of sugar, if we make 6 cups of sugar, so that we can serve for 2 classes instead of our own class. So how many cups do we need to put if we have to serve it for the whole school? So what happens if you have to serve it to your family alone? So, or your family and your neighbor's family, so that you put only 1 cup of sugar. So how many you should reduce on the other things? So eventually they get to understand what is part to part and what is part to whole very clearly. And the next is for the measurements, as Bama was talking about. So here we measure, again, going back to the same measurements with our bodies, we start measuring our own foot to our height. So what is the ratio between our foot and the height? And similarly, what is our ratio? And so go and measure our friends' ratio, foot to height, parent, teacher, and siblings, and figure out that pretty much mostly the ratios are very similar. So they get to know that, so similar ratios are always similar. So that's also another idea which they will get it. Then if there is a musician in the class or who can play a guitar, or even a flute is also a nice one. So where they can understand what is a higher frequency. Ramesh, the next slide. What is a higher frequency? What is a lower frequency? Once they get it, the length of the fret to the frequency of the note, it's inversely proportional, and that they can understand. So the longer the fret, the lower the frequency. And when the fret is like really, really short, then you get a high frequency, high note. And so that also they get what is an inverse ratio. And if you move on to the next, there you understand this is something we can get the formula from the children itself. So we have played, and then we have cooked, and then we have also measured with our bodies. Then we have played some music in the class. Now we'll go out to the ground and start running and walking. So here have 3 columns. One is the way we walk, call it as speed. So a slow walk, a medium walk, a somewhat fast running, and a really fast running. Have 4 categories. Have children on the ground and have a timer, start from one place, go to the other end and start counting. There is the timer girl will give us the time, and then we start writing down. Once all these data go into the board, ask them what is the relation between all these numbers. What happens to the speed when distance is not changing, but the time is changing? Then have them run for the same time and see how long they can run or how short it becomes, the length. So the time is constant, and then so the distance changes. Have the speed constant, and in the for different times, what happens to the distance? So all these different things, then they sort of allow the children to figure out speed is distance by time. Once they figure out these things, they will never ever forget. Otherwise we have to put that regular triangle and then S in the top, and then or a D in the top, and then S and T. So that's not something which I find it as a shortcut. But before getting the shortcut, if it gets into them deep inside, then it stays for longer, for sure. And so this is also covered, like so many things. It's just in the math, we cover physics and many other things. So it is very integrated. And the next is, yeah, this is very, very interesting for me. So when we, I don't know if these days, like where the school water tank is, it's not these sort of standalone water tanks. It's usually in top of a building where they don't even know where the water tank is. But try to take them to some common place, maybe a flag post or something is becoming very common in schools these days. So what is the height of the flagpole, and how do we find out? So, or what is the height of the tallest building in the school? So you can let the children use all the tools. Maybe they can just have ropes. Somebody will ask for a long measuring tape. Maybe we don't have, or we do have measuring tapes. Some of these latest gadgets like IR tools or something like that, infrared tools, which the architects use, probably many of these things. But we don't know, maybe there is a Thales in the class, the Thales who visited Giza. So once we realize all these things, sometimes they can climb the water tank shown here, they can climb the stairs, go up, and then start putting a rope all the way down and then come and measure. They can do all these things. But what happens if it's different? We have to measure to the topmost, then we have to do it in 2 parts and then measure it. And if there is a wind, what happens, and all those things. So, but let's have these explorations and go to the class and start talking about Thales itself and what was the story of Thales. So Thales, when he visited the Giza and then looked at all the pyramids, it's in the next slide. So where he looked at the pyramids and then he was quickly going and asking, like, how high is this pyramid? And then within a moment or something, so this is something no one asked. And so the guides and the tour operator and people who are taking around, they never wondered how high is the pyramid. It was always just awesome to look at them. And so when this question came, they all were confused and they wanted to measure and they started walking this side, that side. But immediately said, never mind my question. I knew what the answer is. And when he said that, they kept wondering. And how did he find out that? He looked at the pyramid and all the other things, like people standing in front of pyramid. And then he understood that the ratio of the height to the ratio of the shadow of the pyramid to the shadow of the people, everything was common. since the ratio was common, he understood by the height of the man standing in front of the pyramid to the ratio of the shadow. Similarly, if I know the shadow's length of the pyramid, I will know what is the height. So he sort of walked the shadow's length and he immediately found out what's the height is. So this is something which would just be fascinating. And then again, the next day, you can tell them, go measure your own shadow at a particular time, immediately go and measure this. So because as the time moves, as the shadow moves, it moves for all of us together, all the objects, all beings together. So once they get in that, it's a little more deeper into them. And next is, this is something which we do in the geography. This is the pi thing. So I move to the next one. So this one, the pi is like this is something which I did last year also after this presentation, where I asked children to go measure the cycle tire and the scooter tire and even the school bus tire itself. So they took a rope and then they went all around the tire and then measured the circumference, and also they found the diameter also. So they found both of them and then sort of figured out what is it, how much is the circumference, and is there a ratio between circumference and the diameter? If so, what is the ratio for the cycle's circumference, diameter, scooter, bus, for a larger circle to the smaller circle, even for the plate what they are eating their lunch? And they found out it's as if it's magic that everything was common. And that ratio is the pi, and they could understand that also. And when we do this, it also can lead into what is the formula for circumference and how the area formula came. So when the circle can be divided into different pies and made into a rectangle. So all these things it's like everything is connected together. Yeah, and the next. Yeah, this is something which we did. This sort of drawings we do in kindergarten and in grade 1, 2. But then when we do it in 4th grade, we would have done the geography in the class, where we draw sort of bird's eye view of our class with the where the blackboard is, where the teacher is standing, where the classroom is, and all those things. But we didn't draw the classroom for the classroom size. We drew the classroom in our notebook itself. So we have actually scaled down. But we don't talk about scaling up and scaling down at that age, but we bring the map, and now we focus in the map which is hanging in the class, or bring it to the class and then show what is the scale of the map which is mentioned in the bottom. And Google Maps is something which many parents and teachers use it. So it's not a bad idea to just show in the screen how much when I zoom, then what does the scale factor changes? How does the scale factor changes? And what does it mean? Brings a little bit of awareness into the scale factor. And so scaling up and scaling down, what is it? So they can look at all these things and into the drawings of smaller things. They can also draw. It's also nice to have a magnifying glass, go look at an ant and draw the ant in the book itself, a blown up ant, really like large. So what is scaling up, what is scaling down? We can understand those things as well, the ratios. And yeah, pretty much that's it. But if you have just maybe 4 minutes or something, can I go ahead, Ramesh, or we'll just skip it to the next class or something? Yeah, this is very interesting. At, somewhere in social media, and then like suddenly something came because of I don't know, because we have to talk about ratios or something. So here's this person who went to a pizza shop, and then he ordered for a 9-inch pizza, the larger pizza or something like that. And then the server said, instead of a 9-inch pizza, we don't have a 9-inch pizza, but we'll give you 2 5-inch pizzas. You're getting 1 inch extra. And then he said, I want to talk to the owner of the shop. immediately. And then he called the owner of the shop, and then he came and then sat next to him. And then he started explaining the 9-inch pizza. If we find the area of 9-inch pizza, it is pi r square, and then pi into 4.5 square, which comes somewhere approximately 59 square inches or something like that. And what happens to 5-inch pizza? It's pi r square, pi into 2.5 square. That's roughly 19 square inches. So if you give me 2 pizzas, by claiming that you're giving me 1 inch extra, you're giving me 39 square inches. Even if you give me 3 5-inch pizzas, I'm at a loss because it does not add up to 58. So, and then listening to this, he said, okay, take 4 5-inch pizzas, we are at fault. And the owner gave 4 5-inch pizzas. And then he claimed at the end of the story, guys, take math serious. Otherwise you'll be short of something. It was funny. It was so good. And it was really relating to the ratios also, how it sounds obvious, but it is not. Yeah. Thanks.
Thank you. Thank you, Sindhu. Because one of the questions people keep asking is, what is the practical value which we have for, various topics in mathematics? While I generally refrain and don't indulge people too much in that, because I do believe math, there's a lot of soulfulness to it. There are also some practical value to it, and a lot of practical value to it. One such thing is this pizza, I guess. And like the 3 5-inch pizza is still not good enough to make up for the amount, unless you like the crust so much, in which case you might choose the 3 5-inch pizzas, I think. Moving on, another practical application is, just wanted to spend just a few minutes in terms of Fibonacci practical application. I've been in markets forever. I mean, I've traded markets, even today I do, and I've traded markets for close to now 28, 30 years. Now, one of the things people look for, if any one of you is an investor or plan to be investing, is this. When we talk about markets, I'm talking about equity or stock market, as we call it more generally, markets like that. Now, when prices go in markets, they don't go in a straight line. Okay. So if let us say there is a company which is quite an attractive company and a lot of people want to buy the stock of that particular company, the price of that particular company doesn't keep going up, up and away. What it does is it goes up to a certain distance, and then it's as if the whole market, all the people put together, collectively are taking a breather and wondering, have we done too much? Have we done enough? Or are we at the right price? And invariably, the market seems to think that we have done too much, and it does what is called a correct, which is, let us say price goes from 1,000 to 2,000, and then from 2,000 it will come down and come to a more stable place. From there, it will launch the next wave. Now, how far does it come down is an interesting question to ask. More often than not, I have seen in charts that the Fibonacci retracement is seen as a very important indicator. I will show you an example of how that happens. I'll show you a chart of a very, a company which is a household name for many of us, which is Asian Paints. You can see, the Asian Paints prices started at, well, pretty much a low where the little yellow circle is coming on the left side, bottom left side, and it made a significant move to the upside, and pretty much that particular wave finished at a higher price, and it finished there. At that point in time, like I said, as if all the market participants said, have we done too much? And the market takes a breather, and it comes down, as you can see, exactly, almost exactly, as exact as markets can be, almost exactly to the 38.2. And 38.2 is nothing but 1 minus 0.618. Even retracements like half and 61.8 are considered as very, very important retracements. And you can see the next time around when you break it, it just jumps away and goes beyond that in the second wave. And we can do a retracement of the second wave and the third wave and the fourth wave and so on. And there's a full wave analysis which happens in markets. And sometimes markets are also considered as fractal, where you will see this kind of a pattern, whether you see it on a minute chart or on an hourly chart or on a daily chart or on a weekly or on a monthly. And these patterns seem to repeat themselves, which is like a combination of fractals, Fibonacci, and some amount of psychology as well involved in it. All right. So investing is not really a pure science. It's a social science. It's a group of people coming together and creating a certain environment in which people who want to buy can buy from people who want to sell. It's more like a marketplace. And the Fibonacci retracements are very, very important in markets, not just 38.2, even 23.6% retracement is considered as very important. Take a pause and ask this question. Can you figure out why 23.6 could be interesting or important? Well, we don't have time. I mean, we are rushing through syllabus, so to speak, and we don't have syllabus.
38% of 38%.
Yes, yes. It is in fact 61.8%, which is one of the retracements of the 38.2. Okay, so in fact, there are charts where you can actually see some kind of a fractal analysis being shown as well. So you take the 38.2 and take 61.8 of the 38.2 and then go inside and inside and inside for you to find out what are called supports and resistances, which we read in newspapers often. Okay, and well, the space of investing, like I said, I mean, there are lots of these mathematical applications which are there inside the space of investing, and there are lots of mathematical modeling examples. Even in risk management, quite a bit of that is used, where we are able to teach a machine how to learn from these patterns, whether it is machine learning or artificial intelligence, or more broadly data science as we call it, are able to leverage some of these key concepts which are present in the field of mathematics and use it in trading as well as risk management. Those are just a few words as far as practical application is concerned, and we can take questions and then move into Priya's case. If there are any questions, we can go ahead now. Okay, we'll take the questions in case there are any right at the end. Priya, you're on?
Yes, sir. Good evening. Am I audible?
Yes, you are audible, Priya.
So can I start?
Yeah, I'm going to share the screen where I have just copy pasted what you've